This presentation will look at the key principles of availability and redundancy in Cisco switching. Basically, there are 6 main components to high availability. That's typically network device reliability. We need to make sure that devices that we have operate correctly. Device redundancy. One way to make sure that we have good availability is if one network device fails, there is a backup for it. There's link redundancy, and that's about running redundant links to make sure that if one link fails, then the other link will act as a backup for it. It can also be used for load sharing too. We need fast convergence. Any small changes in the network need to be converged quickly. We need good network design, a good layout. We need to understand where we should put our network equipment in order that we have good availability, and we also need to have a well-documented network. It is these 6 principles that will allow us to maximize the uptime of the network. The 2 main types of redundancy that we typically have is chassis redundancy, and that is where we use a backup devices which are physically separate from each other, and then we would typically create alternative routes between the devices. We can also have component redundancy. With this, we might have redundant supervisory engines, hot swappable modules, redundant power supplies, fans, and so on. It is often the case that we need both types of redundancy. We would typically have redundancy with inside the switch, but we would also have chassis redundancy. Typically, there is some cost benefit analysis done on the equipment, and it's normally the case that a redundant switch proves to have a greater benefit than the actual cost, as a failure of the network can be extremely costly in terms of lack of productivity. So we can either create this at the core layer, at the distribution layer, or within inside the access layer. So our chassis redundancy will have backup devices, and we can see here that these devices will typically be used in a load sharing architecture anyway. And in component redundancy, we can have redundant components within inside our chassis, our switches, so that there is less need for these backup routes. You see here, these are lacking and these 2. The problem with this type of architecture is obviously that a power failure to the switch could actually cause the parts of the network to fail, whereas in this one there are alternative routes around switches that were to fail. So for component redundancy, we get rid of the single point of failure. We also help in convergence issues in that we have a single switch which is dealing with the redundancy, and also that switches can be distributed. So the typical types of redundancy that we have is that we have alternative supervisory engines. We can see here we can plug another one in here into slot 1. So if the main supervisory engine fails, then the secondary one can actually take over instead. We can have hot swappable modules. Even though the power is still on, we can actually plug modules in and out on the case of a failure. Power supplies are an obvious point of failure, and we would typically have two power supplies, one of which is redundant. If one fails, then the other one will take over. And we also have redundant fans, where if a fan fails, then the device might heat up too much and fail, as heat is typically a stress factor for the device. So for this we have multiple fans, so if one fails, another one will kick in. The downside of component redundancy is that the components are typically in a standby mode and aren't actually used, so it can be seen as inefficient. It's also fairly expensive for our switches in that we need multiple power supplies, supervisory engines, and so on. The major fault, though, typically is if the whole device fails, such as a lack of power, then it doesn't matter if we have backup engines and backup supplies, then the whole switch fails. It can also suffers from backplane failures. If the backplane fails, then the whole device will fail. Chassis redundancy allows us to create backup routes and also to have backups for our switches. So in this case, if this switch was to fail, then this device can still communicate with the other device through this switch to there and then on to there. So we can see here they also have redundancy at this layer, where if this switch was to fail, then the node can still connect to this switch, and so on. What we need, though, is that we need a fast convergence of switches. When a switch fails or a route fails, then we need the network to reconverge and determine the best routes to each of the destinations. So we thus need fast spanning tree. There also needs to be intelligent routing protocols such as OSPF and ERGP to allow for fast layer 3 convergence. These are typically event-driven routing protocols and allow for fast changes. The advantages are many. There's no need for high tolerance inside of each of the switches, as the backup will provide an alternative route. The configuration issues are overcome in that we can have a fairly similar configuration for each of our redundant switches. The switches themselves are typically geographically distributed, so that a failure of power in one area will typically not cause an outage on another geographical area. We can also load balance on these switches. The disadvantage is obviously that more connections are required and that more devices need to be managed. A key factor in any switch is the power supply. If the power supply fails, then the whole switch will fail to operate. So it's important that we have power supply redundancy. Typically for this we have two UPSs, in this case 1 and 2, and we supply them to the rack. This gives us the opportunity to actually share power between the two, but also if one fails, then the other will take over. So the command that we have is power redundancy mode, either combined, where we will take the power from both, or in a redundancy mode. To show the power, we can actually run the command show power. So in this case we can see that we're running on redundant mode. There is 3.8 kilowatts available from one power for both power supplies, and 2.268 kilowatts are actually used at the present time. So we can see here the two power supplies are listed, and we can see the state of them is actually on. The supervisory engine redundancy allows us to switch in an additional supervisory engine into one of the slots. So we can see here, this is the slot here for the main supervisory engine for a 6500 chassis switch, and we would plug in our redundant switch engine here. The switch engine itself contains a root processor redundancy, where we have about 2 to 4 minutes for a switchover. It has a multi-layered switch card, feature card, and a policy feature card. It's also possible to get a faster redundancy system with RPR Plus, where we can have 30 to 60 seconds for the switchover. And the switchover occurs either when we configure it from the command line interface, when there's a failure on the main switch engine, supervisor engine, or where there's a lack of clock synchronization between the primary and the secondary. When a switchover happens, the secondary supervisor engine cycles all the ports to re-enable them. We can show the modules that we have in our switch. So in this case we have the main supervisor engine here. We have the multi-layer switch feature and a redundant supervisor engine, along with a multi-layer switch feature in module 16. So our modules each have a serial number, and then we can actually see the firmware version and the MAC addresses for each of the switch ports. Here we can see our two supervisory engines, our primary and our secondary. We can use root process redundancy, or we can use root process redundancy plus. RPR plus gives us much faster switchover when our main supervisory engine fails. So in this case we say mode RPR plus, and then that defines the RPR plus, and then when we show our redundancy it should actually confirm that we're running on RPR plus. We can see here the switchover time is 8 seconds. We also have uplink interfaces, and it is these uplink interfaces which are called upon when the supervisory engine fails. So in this case we might have one connected to one slot and another connected to another slot. This shows an example of a card with 10 gigabit uplinks, where this one only has 2. And the gigabit uplink on the SE, the secondary supervisor engine, is still functional even when the card is in a standby mode. Another protocol which is used to be able to sense when there are changes and to automatically discover changes, such as when a switch fails, is gateway discovery. And with gateway discovery, the device can use a protocol such as ICMP router discovery protocol, which uses a similar action to ping and trace route to be able to discover the new gateways. Unfortunately, it can take between 5 and 10 minutes to actually properly discover it. Another protocol which is used to discover the gateway is proxy ARP, and with this method, the switch is continually listening to ARP requests on the devices, and when this node is using, say, this switch as a gateway, then this switch can actually proxy the ARP so that it actually changes the destination to pretend to be the default gateway. As far as the node is concerned, it is still communicating with the same gateway. In Layer 3 redundancy, we have hot standby routing protocol, HSRP, single router mode, SRM, and the load balancing protocol, GLBP. The hot standby routing protocol is a method that we can use for Layer 3 redundancy. With this, we create an HSRP group. So we can see here that we have two RPs, 1 and 2, and then these are grouped with inside a single HSRP group. Then we define a virtual IP address and a virtual MAC address for our gateway. So as far as these nodes are concerned, they will communicate with this gateway. So if this device was to fail, then this device will still be able to route from that virtual gateway. Same again, if RP2 fails, then RP1 will service this gateway. So we have a virtual IP address and a virtual MAC address. We can also do the same for different VLANs. In this way, VLAN 2 has one gateway here, and HSRP Group 1, VLAN 1 has these two devices, and again we have a virtual gateway for VLAN 1. Basically what happens is there is an election process at the start of the protocol, and then a priority scheme is used to support the preferred RP. So in this case, RP1 may be preferred over RP2. RP2 may be faster or have improved switching capabilities and so on. So the election process, RP1 will be the gateway for this group. So we can see here that the election process involves identifying their group number, and then we can actually identify what the standby address is and the standby priority. The way that it operates is that an active RP continually sends out to the network, typically to the standby RP, hello messages, which are multicast. If the standby RP does not hear a hello message for 10 seconds, it will then take over. The standby RP itself also sends out its RP messages, hello messages, to make sure that other nodes know that it is alive. In this way, it can take up to 10 seconds for the network to handle a fault on the active RP. So the key part of this is that they use multicast messages to be able to send one message but to many nodes that are receiving. The port which it sends on is port 1985 on this address, and the time to live is set as 1, which stops this multicast being broadcast into other networks and swamping the whole network. Basically the message has its version number, the state, the hello time, the hold down time. The hold down time is the amount of time it will take. It will wait, the standby will wait before it will take over. So in this case 10 seconds. The priority of the RP, its group number and its virtual IP address. The basic states that we have is that we have the initial state. There is then a learning state in which RPs listen for all the RPs on the network. And then there is a listening phase to listen for the groups and their virtual IP addresses, and then on to a speaking stage at which they will create an election to let the RP which is the most preferred. After the election, they will either go into a standby mode or they will become active. The configuration on a router, if we were to use a router, is basically to define the IP address, and then we define the standby group, in this case 2, with a certain priority, and the secondary IP address. We can then go on to define the hello time, as we've seen 3 seconds as a typical default, and the hold down time of 10. Same thing happens on our switch, but we create it typically for each VLAN. We create its primary IP address, its group number, its priority, and then what its secondary address will be, followed by the hello time and the hold down time. The protocol which is used is VRRP, or the Virtual Router Redundancy Protocol. It's similar to HSRP, but it is an open standard. For this we can specify again a virtual IP address, and then we use an IP, the IP protocol and the IP header of 112, and a standard multicast address. So with this, on Ethernet 1, we define the priority, we make it preemptive, we can define our timers, and then we can actually define if the timers are learnt. Another protocol which is used is single router mode redundancy. With this we have a dual multi-layered switch feature card which is installed on both the primary and the secondary supervisory engine. Its advantage is that we only need one IP address for the gateway, and only one RP is active at any given time. The configuration is shown here. We define redundancy, high availability, and single router mode. With global load balancing, we can actually balance the loads between redundant routes, and we have one active router and up to 4 other devices. The advantage with this protocol is that the devices can learn the virtual addresses of each of the end stations. It is, though, Cisco defined and is an alternative to HSRP. With server load balancing, we can get load balancing again with a virtual server that each of the endpoints used. The advantages of this is it's fairly simple to work on one of the servers. Real addresses on the network aren't actually used, and it distributes the handling for end stations, and it's fairly easy to move a group of servers. Principle which was touched on in this lecture is the principle of multicast. Normally when we communicate over the internet we use unicast, where one node sends to another node directly. We can also have broadcast, where we use a single address to broadcast to the whole of a network. Probably a more efficient scheme is to use multicast, where only subscribed hosts will listen to a multicast transmission. So in this case, only 2 of these hosts have subscribed to this multicast message. The advantage of this is that we have scalable bandwidth from 0 to many. We can have registration of our nodes onto a multicast message, and it supports the participation between a node and end hosts. Unfortunately, it only has a best effort delivery. Typically we use a class D addresses, we have local addresses, and we can also have global addresses. Typical addresses that are used: 224.0.0.1 are for local subnet multicast. .2 is for RPs on a subnet. 5 is used for OSPF routers. 13 for PIM RPs. The protocols that are typically used with multicast, as we've seen, are IGMP for client registration, PIM for multicast routing, and IGMP snooping, and for CGMP to control multicast traffic.